Good afternoon. My name is Guillaume Bernat from Rapita Systems, and I'm here with Olivier. Olivier?
Hello, everyone.
Hello. We are here to present our webinar on verifying multicore RTOS partitioning of DO-178C with an emphasis on CAST-32A. Thank you very much for attending. So the agenda and the objectives of today is that we'll first talk about an introduction of multicore processors, what's CAST-32A, and the outline of interference channel analysis. Now I'll pass the token to Olivier. We'll talk about how we can get support from the real-time operating system for mitigating interference and by the use of partitioning. And then I'll take the token back and we'll go deeper on how, why the RTOS partitioning mechanism needs to be verified and how to do it. And we're going to finish the session with a demonstration of how the process that we discussed is implemented and how the numbers look like. There will be a session for questions and answers later on. Please use the question and answers text on your right of the panel, and then we'll collect those questions and we'll address them at the end of the session. If you have a question that is specific to either myself or Olivier or Crystal, which is the colleague in the demo, please say so. So let's do an introduction. First, a brief overview of Rapita Systems. We specialize on on-target software verification for solutions, which is tools and services for critical embedded systems. And the issue of timing analysis has always been central to our work. The company was founded in 2004 as a spin-out of the University of York. We are close to 60 staff with quite a number of PhDs and doctors that provide the advanced solutions that we are presenting in particular today. Since 2016, the company is now owned by an American company called Law, and as a result of that, we also set up operations in the US for our partner company, Rapita Systems, Inc., where the headquarters are still in the UK. We also have offices in India, plus distributors around the world. What we are here today is to talk about multicore processors. If you attend this session, it's because you already know what are multicore processors and why you need them. But just as an overview, is that there is an evolution from federated systems through ANA to advanced avionics, and these has been also driven to increase capabilities, reduce weight and cost and power consumption. And also, there's also an increase on the functionality and therefore computing performance that can only be realized by the use of multicore processors. The other dimension is that avionics domain is a tiny market compared to the mobile phones gaming industry. Therefore, having specialized processors for specifically addressing the safety critical requirements is a challenge. There are some solutions that custom-made processors, but the default one is that avionics industry has to use the processors that have been available and developed by chip manufacturers. Single core processors are still a preferred solution if you can, much more simple, CAST-32A doesn't apply, but there is the risk of obsolescence. So there is, all this pushes the industry to upgrade to the path of providing or using multi-core processors. Multi-core processors are complex beasts. I remember the time when we started looking at the first single-core processors, timing analysis on a 6020 or 750, block diagrams. They are not even at scale. If we put the scale from Power 750 compared to NXP, it will sit probably on the space where you have the little T here on the first cluster on the 2080. So the exponential growth of complexity means that they are very difficult to understand. And not even, we'll say that even chip manufacturers have a full understanding at the cycle level how processors work. And that has driven certification authorities to provide additional objectives to perform the verification. Now, the key focus we try to understand here, and this is the whole concept, is the issue of interference and the impact that it has. Interference, as CAST-32A definition is a property that can cause, an interference channel is a property that can cause interference between applications. And this interference is extra delay, which in cases where by running two applications on two different cores, they are barely affected. Others may be affected by a factor of 5, 10, 20. The question is, the impact can be very, very high. Therefore, there has to be some level of quantification. The traditional notion of shared resource and interference channels is the use of memory, buses, caches, and when they are shared, that resource is slows down in a direct way, just because it's not available, but also by side effects, for example, changing internal state and then the reprogramming of that state also causes delays. So as part of the CAST-32A, or the effort of CAST-32A is on providing a series of objectives to complement the DO-178C, which we understand that was designed, conceived before the time of multicore processors. And there are two of the objectives that we're going to be talking in particular here. There's a few more I'm going to explain later. But the key one is MCP-1, which is basically saying you have to do worst-case execution time analysis to guarantee that all applications will finish within allocated time. The means to do that is understanding what are the shared resources. And there's a specific objective on CAST-32A called MCP Resource Usage 4, which requires you to identify the resources, how it is allocated, and verify what are the demands on those resources. So what is the load on the bus? What is the impact of interference on contention of the cache, but also we want to extend that to other what I call hidden interference channels. The impact, for example, that a processor when it overheats because it's doing too much floating point calculations may have a side effect of lowering the clock frequency and therefore delaying the whole interference. In that case, a floating point unit could be called as a shared resource because it has a potential interference channel. Please know that in all the concepts described here today, the notion of worst-case scenarios and worst-case behaviors and guarantees is implicit. So the DRAM is not an overview on CAST-32A, but it's important to put as a context what are the objectives and what are the implications. So there are two objectives related to planning that the applicant will put as part of their PSAC or the PHAC. There are objectives related to resource usage that are part of configuration settings and how to demonstrate that an accidental alteration of this configuration settings has been properly mitigated. The key ones are the issues on identification of resource usage, which is interference channel analysis, and its quantification. There's two aspects here that is important to reflect. Is one aspect of the analysis is what we call hardware characterization, the understanding of what are the actual impact of the potential shared of a resource. Let's say, for example, that the resource that you want to identify is access to the coordinate fabric on a D2080. Understanding where the execution time or the transit on an empty bus or bus that is only used for one core is in relation to when there's maximum traffic. This is one of the activities we do in as part of research users 4 and what we call hardware characterization. And this can tell you which are the resources who have a potentially negligible interference, and therefore they can be not ignored, but accepted that they don't need to be mitigated, and which are the resources that have a potentially huge impact on the interference, and this one needs to be mitigated or avoided. There are two additional objectives